Hey guys, this is John. In today's video, we'll be solving Laplace's equation inside a cylinder. This is the 6th video in a series about solving Laplace's equation on various types of surfaces. And let's get started by reading this problem. So we're told to solve Laplace's equation on inside a cylinder, with no surprise. And we're told these several boundary conditions here. So let's just highlight them. On the top, we're told that we have this very crazy looking boundary condition. On the bottom, we have 0, and then on the lateral sides of the cylinder, we're at 0. Okay, so the first step to approach this problem is to draw the shape. Okay, so we know we have a cylinder, right? So let's draw the cylinder to my best of my drawing ability. Let's mark this as the center of the cylinder. The cylinder has a radius of 1. Okay. On the bottom of the cylinder, so for u r theta 0 is equal to 0. Let's draw some coordinate grids. So this is the z-axis. I'm not really going to mark the x and y-axis because we're technically in polar coordinates. Well, I mean, yeah, x and y is fine. But we're going to be modeling the cylinder in polar coordinates. The lateral side is equal to 1 theta z equals 0, and the top, so the cylinder has a height of h, is equal to this crazy looking relationship here. So the way to interpret these boundary conditions, right, is that so for example, for this bottom, well, I mean, they basically tell us like where they are, so on the lateral side, bottom and top. But you can sort of like understand this by looking at like where we are evaluating at. For example, on the lateral side, we're evaluating at 1, so around the entirety of the edge of the circle for any theta and any z. So if you imagine rotating around the edge of the circle for any theta or z, you're imagining basically the lateral side of that cylinder. Okay. So now step 1 is to separate the variables. But we're conveniently given the separation variables for, the separation for this Laplacian. Remember that Laplacian u is equal to 0, and we're given the Laplacian above, but we're also told that u of r theta z is equal to, let's see what they define it as, f of r, g of theta, and then h of z. And then we're told that each of these individual differential equations is equal to h double prime is equal to lambda h, g double prime is equal to negative mu g, and then the last one states that r times r f prime prime plus lambda r squared minus mu times f is equal to 0. So let's take a look at these individual differential equations, and before we proceed to steps 2 and solve them, let's try to understand them a little bit. So remember in z, we have, that's a terrible half, let's try it again. We have non-homogeneous species. So therefore, we want exponential solutions in z. In theta, we have homogeneous species. Remember that since we have a full circle here, we have homogeneous boundary conditions that basically are the periodicity boundary conditions, as I called them in the previous videos on the circles. And periodicity conditions basically state like the continuity of the circle. And in theta, consequently, we want oscillatory solutions. So looking at z here, in z, this diffie q will give us sinh and cosh, right? So exponential solutions. In theta, we will get oscillatory solutions in cosine and sine. So these two differences have satisfied our necessary conditions. The lateral side satisfies this boundary condition, this third equation right here in R, which is a little bit different. So we'll get there eventually. But for now, let's solve the differences. Solve the differences. Okay, so let's solve for h first, h of z. So the differential equation for h of z is right above there. So the consequent solution for h of z is going to correspond to h of z is equal to c1 sinh square root lambda z plus c2 cosh square root lambda z. We're given a boundary condition that at 0 we're equal to 0. Remember the graph of sinh and cosh. I'll draw it real quick over here. Sinh looks like this, and cosh looks like this at 1. So remember that if we evaluate sinh at 0 is equal to 0 and cosh at 0 is equal to 1. So therefore C2 must be equal to 0. Unfortunately, we can't really reduce this any further because the other boundary condition is our initial condition, and that's not a homogeneous boundary condition, so we can't really find any lambdas from this, but we can eventually find the lambdas from one of the other differential equations. So this is basically all we can get out of the h of z. You could also technically case out, I don't know if this problem tells you the eigenvalues. Yeah, this problem doesn't necessarily tell you the values of the eigenvalues straight off the bat. But if you did, we're going to move along now because we can find the exact values of lambdas later. So just take my word for it, and then we'll eventually figure it out. So let's look at the g of theta terms now. G of theta, the differential equation here is just second derivative of g is equal to negative mu g. And since we have periodicity boundary conditions from our table, periodicity boundary conditions, and this will give us solutions of sinh and cosh. So g of theta is equal to C2, let's call it C3 for different arbitrary constant. C3 sine, let's call it m theta, plus C4 cosine m theta, where mu is equal to m squared. And I basically got this solution from the fact that the differential equation we were given above satisfies the table that we usually see for 241 problems. And we should also note that m starts from 0. And m can be any infinitely large number, any infinitely positive or 0 number. Yeah, okay. So now let's take a look at the f of r terms. This is somewhat more interesting. So hopefully you guys have seen Bessel's function already, but we'll work on looking at all pieces of it. So let's first just write out that same exact differential equation. I like to write it out in its like total form. Yeah, let's try it again. R ddr times r df dr plus f times lambda r squared minus mu is equal to 0. So if we plug in the value of mu we just found there, we can do that nice and easy, just a quick substitution. Let's expand this side of the equation right here, and if we take the appropriate product rule derivatives and stuff like that, we should get this form. Okay, so the next step to take here is completely unintuitive and is pretty much only possible if you have seen this before. So what we're going to do is we're going to redefine our variables here. So we're going to do a change of variables. Let z be equal to the square root of lambda times r. So consequently, this becomes z squared minus m squared equals 0. If we do a full change of variables and change the derivatives appropriately, what we should find is that we're equal to z squared and d squared df dz squared plus z df dz. Sorry about that. Okay. So now this equation right here is completely unknown until you guys have actually studied it, but I believe you guys should have a sense of what Bessel's differential equation is now, but this is called Bessel's diff EQ. And the solutions for Bessel's differential equation are these two functions here. F of z is equal to, let's see which constants we're on, C5, J, Jm of z plus C6Ym of z. So what we're going to do now is we're going to try to eliminate one of these j and y's. Before I arbitrarily throw these at you, what we're going to do is we're going to draw a quick graph of them for the positive numbers. Okay, so quickly, this is very rough and arbitrary, but here's sort of like a sense of what j0 and j and y look like. So for j0, j0 intersects at 1, specifically 1, and sort of looks like an oscillating decaying function right here, something like that. That's j0, and then the rest of the j, higher order j's kind of look like this, and blah blah blah. Basically, the big point to take away from all this, right? Let's call this j m something, and then this is also j. The basically whole point of what this very poorly drawn graph is trying to show you is that j of m for any m greater than or equal to 0 is defined at 0. Okay, I'll write that out explicitly. J of m is defined at 0, i.e. not undefined. So this pink line right here sort of represents what y of m looks like. So y of m kind of looks like this big slurpy thing, and then just kind of decays as well. So the big difference to note between j and y here is that y of m is undefined at 0. Okay, so how can we sort of apply this? So do you guys remember the boundedness condition? Remember that at the center of the circle, right? At the center of the circle, we have a singularity. So the appropriate way to write this is that the limit of u r theta z as r approaches 0 is less than infinity. The limit of the absolute value here. So therefore, our function for f of r has to satisfy this limit right here. I kind of use bad notation. I let my change of variable be equal to z. Let's call it zeta, something like that, with like a z bar just to differentiate from the z from earlier. So yeah, so this zeta is different from the z I've defined for the height from earlier, so my bad on that, but let's continue along. So remember that zeta is equal to square root lambda r, right? So we can substitute it back into the original. So remember this is an f of r function. So we'll just copy and paste this down here. I think that might have carried the asymptote line. Oops, let's erase that. And then f of square root lambda r, square root lambda r. So applying this limit right here, we're basically saying that as r approaches 0 for this function r, we have to be less than infinity. We cannot be undefined, okay? So if we plug in infinity, just as a way to do this, just to show it in a sense, I guess, infinity plus c6 ym infinity. The problem that arises is that, at 0, my bad. The problem that arises is that at 0, right, so for 0 right here, ym is undefined, whereas jm is well defined at 0. So consequently, we're going to force c6 to be equal to 0 so that we satisfy the boundary condition. So consequently, f of r is just going to be equal to c5 jm square root lambda r. Great. But there's another thing we can do. We can actually find the direct value of lambda from here. How can we do this? Let's apply the lateral boundary condition. Remember that at the lateral edge of the cylinder, we're equal to 0. So at radius 1. So let's plug this in. So f of 1, we're equal to 0, and therefore our Bessel function is also equal to 0. remember that if we let this constant be equal to 0, then we'll just have a trivial solution. So we're going to force this to be non-zero and look for zeros elsewhere. So what we're going to do is we're going to define the zeros of the Jm function, okay? So bear with me as I write this out. Square root lambda r is equal to, let's call these zeros alpha mn, okay? So alpha represents the nth zero of the Bessel function, and I'm going to write this again, where alpha mn represents the nth zero of the mth Bessel function. So I'm going to draw j of m again, but I'm going to draw j0 specifically. Okay? So this is going to represent j0, and j0 is equal to 1 at 0, at x equals 0. So this is the x-axis. So each 0 that we're referring to is what I'm making a point as right now. So this would this 0 right here would correspond to alpha 0, 1. This 0 will correspond to alpha 0, 2, alpha 0, 3, alpha 0, 4, and so on and so forth. So what I'm just trying to say is that we don't necessarily know the pattern of where each 0 of the Bessel function is. The converse to this is that when we do this with a sine function, right, each 0 of the sine function is nice and evenly spaced by a factor of n pi, whereas the Bessel function has arbitrarily spaced zeros. So we're just going to call these zeros alpha mn, so some arbitrary 0. And therefore, lambda is going to be equal to alpha mn over, oh, this should be 1 right here, sorry, because we're evaluating radius 1. So lambda is just going to be equal to alpha mn squared. Cool. So now, where do our lambdas begin, right? Our lambdas begin at 1. And why is this? It's because we don't necessarily define the first 0 of the Bessel function to be the 0th 0. We're going to call it the first 0 just for notation's sake, like that. So now that we've found f of r, we found h of z, and we found g of theta, we can proceed to step 3. Just put it all together. Remember that u is equal to the product of f times g times h. And let's first take a look at the lambda equals 0 case. But since lambda isn't equal to 0, we don't really need to worry about that too much. So let's just put everything into one big summation. So n is equal to 1 to infinity, and m can start from 0, right? So m can start from 0, so we're going to have technically a separate term, but we can just consolidate it all into this big summation. So let's call this big constant that survives every term to be a-mn, because it has a double dependence on the summation. Then we're going to have this jm term. J of m is equal to square root lambda, so alpha mn times r times one of these g theta terms. So let's do sine theta first. Sine m theta. Okay. And then sinh. Let's see what the sinh is. Sinh is square root lambda z. Okay, where lambda is equal to alpha mn. So alpha mn z plus the other term. So we're going to call this constant coefficient bmn times jmn again. So same exact here. Times cosine of m theta times this another sinh term. Make that a little bit smaller. Okay, so I'm going to annotate each of these terms real quick so that you guys can see exactly where I got them from. So this term right here is our f of r term. This is also our f of r term, same f of r. This is equal to our h of z. And both of these combined right here form our g of theta. So when we have to multiply all the possible product solutions together. So now let's go on to step 4 and apply the initial condition. I'm just going to copy and paste this on here in preparation. So step 4 is apply the initial condition. So we're told that at a height h, so at the top of the cylinder, we equal to this relationship right here. And now we have to plug that all in, and that's going to be annoying, so let's be careful. So the problem has defined their notation a little bit differently, but we can go along and try to match what they did, essentially, and not really have to worry about that too much. So we're going to be equal, let's move this over a little bit, equal to this at height h, so we're going to plug in the h here, plus the BMN terms. Another height h. So I believe that they called their zeros here z's. I'll circle that in a different color. So let me see in their initial problem. Yeah, so they denoted the z's of the Bessel function. Sorry, they denoted the zeros of the Bessel function by z. So let's just change up their notation into ours so that we can be more a little bit more clear. So remember that z is equal to alpha. So we're just gonna replace this with the letter alpha. I'm just gonna keep it in green for notation's sake. And they seem to have used everything else we used. Okay. So let's take a quick look at what they have defined here and try to match it up very closely. The first thing you guys should notice on the initial condition is that there's no, I'm gonna write in purple, no sine and cosines. Okay, and that only corresponds to when m is equal to 0. Right, so therefore our right-hand side of the equation has to be valued at 0. And note how there's no summation on m. And that's because they're currently valuing at a specific value of m. So now let's reduce our right-hand side of the equation so that we're specifically at m equals 0. So now it's going to be equal to the summation n equals 1 to infinity, but now we're specifically looking at m0. So a0n times j0 alpha 0n r sine of 0 sinh alpha 0n h plus b0n, and I can just copy and paste this basically, times cosine of 0 sinh alpha 0 h. Remember that sine of 0 is just 0, so we can just literally cross out this entire term right here. And now we're only looking at the cosine dependent terms, or the b0 dependent terms, because cosine of 0 is just 1. So let's move everything else down here, because this is all we're looking at, essentially. And another really good way to notice this is that on the initial condition, we're actually told that we're looking at specifically j0, and j0 here in our general solution has only dependence on m for the order of the Bessel function. So we can make pretty good conclusions of like what the value of m is going to be. So remember that the initial condition has to be equal to our general solution, or it has to satisfy that over here. Okay. Oh, so this is another z right here that we forgot to get eliminated and change to alpha. That's okay. So now, notice that the summations are equal to each other. So a rule is that, like, hopefully, the rule that you know is that if two summations are equal to each other, we can just equate the insides of the two summations. So let's just get rid of the summations and look at the insides. Is equal here. Notice that these two j0s are the same, so we can just cross them out here. These two cinches are the same, so we're going to just cross them out as well. So what does this tell us? This tells us that b0n is equal to 1 over n. And that's basically it. So maybe they could change up this problem a little bit and maybe make, like, instead of 1 over n, like 5. So make it a little bit less arbitrary, but this is basically saying for any n, any value of n we have, we're just going to be equal to 1 over n. Don't over-interpret it. But now we can put everything into a final solution. Nope, let's not put that there. So the final solution is going to look pretty nice, actually. So remember that our general solution looked like this big thing over here that I'm about to circle in green. This was our general solution. But now we only have BMN terms, and we know for specific m values that we have that BMN term. So let's write it out. So u of r theta z, is going to be equal to 1 over n. So we have to make sure we have our summation here, so we don't know which n we're looking at actually. So n equals 1 to infinity of 1 over n. So that's our b0 n term times j0, because remember we're looking at j0, of alpha 0 n r times cosine 0, which is 1, times sinh alpha 0 n of z. And we can quickly check this satisfies the boundary condition by plugging in h, and we notice that everything matches up and eliminates properly. I'm just going to quickly annotate this. This corresponds to b0n, and yeah, and this would be our final solution. Yay. Yeah, so this should demonstrate to you guys how to solve a standard Laplacian inside a cylinder question. Please let me know if you guys have any questions, comments, or concerns in this comment section below, and good luck with your studies.